This is one of the toughest drill bits made here. That is serious precision. These small holes in the steel body will hold the carbide inserts. Carbide inserts. Workers call them carbide buttons. Each one strengthens the cutting face and helps the bit drill faster. That gives it real power in mines, quarries, and rock drilling. That strength matters every day. This carbide is hard. It lasts where normal steel wears out. It handles heavy pressure and high heat in brutal industrial work. But moving this heavy drill body is never simple. Even the lifting slings use high-strength synthetic fiber. They grip better than chains and give the crew more control. Once the body is locked in the chuck, the setup must run perfectly true. But cutting does not start yet. First, the crew checks the tools on the side turret. These cutters are made for hard steel. At least that is how workers here describe them. Shaping the drill body takes longer than most expect. It takes about 2 hours to reach the final shape. Smooth surface with a clean metal shine. Every mark is checked, but measurement cannot be skipped. Under 0.01 millimeters is the factory standard here. For ordinary parts, that precision is not needed. But this bit needs a tighter standard. Now let us look closer. From start to finish, this single metal piece loses over 100 kilograms. The first bit was too large to show the details clearly, so they use a smaller model. First machining stage matches the larger bit. It is cut on a heavy setup, but the whole job must use cutting oil. The oil cools the tool and washes away metal chips. So this step uses a lot of cutting fluid. Luckily, the separator solves a major problem. Watch the chips leave the cut. The machine sends them into a bin. At the same time, oil drains to a tank. The system looks complex, but it works. That is how they hold 0.01 millimeters. Is it as exact as the first step? Not quite. The pin joint allows tiny clearance. But that clearance is very small, almost invisible to the eye. Next, the tool cleans the edges with coolant. This is only for the top and bottom edges. The center contact points are left untouched. They already meet the surface standard and are ready for the next step, but without carbide buttons. This is not finished yet. So now, the crew begins the key step: installing the carbide buttons. First, the shaped body is secured in the 3-jaw chuck. Then the operator adjusts it to match the body curve. Set. The chuck is tightened. It locks the piece. This step is very detailed. Drilling the holes may need several cutters before one hole is finished. The tools include finishing cutters, face mills, and ball end mills, but they are not used yet. First, the holder takes a center drill. This tool marks the hole before deeper drilling starts. It does not make the full cut. It guides the drill and reduces error. That center mark matters. Under high-pressure coolant, the process stays fast and clean. Every marked point will seat a carbide button. Look closely, and you can see the CNC controlling every move. That means every position has very little room for error. You see, a mining bit needs more than a finished face. The side surfaces also matter. So the machinist must finish the outside diameter. How do they cut this heavy steel part? To the exact size needed. It must leave room for the buttons. In reality, the hole cannot match the button size. If it did, how would it hold? It would fall out. So each hole is slightly smaller. After installation, the button locks tightly in the steel. But that raises a question. If the hole is smaller, how can the button go in? Keep that in mind as we move on. After outside machining is done, the crew blows off debris. Then they place the body on an open rack. As mentioned earlier, holes alone are not enough. The carbide buttons must still go in. So how do they install them and keep them secure? The answer is heat. Controlled heat changes the metal. The key effect is thermal expansion. The holes and outer walls expand together. But one condition matters. Preheat must stay at 500 to 700 Celsius. It may not glow red, but you can still see a darker surface tone that comes from preheating. If the heat goes higher, the steel would glow red, but that is not the goal. Drill bits come in many shapes and sizes. Are there other versions? Yes, there are. This shorter one is a good example. Only the height is reduced. The head keeps its working size. Then the body is leveled. Now installation can begin. Now the final buttons go in. They go in while the steel is hot. As the heated wall expands, the carbide buttons slide in more easily, but for the last pieces, a hammer is still needed. Some press cold. Here, heat helps, but the hammer still matters. It is learned by hand, not from a manual. And in this workshop, it shows. Without that experience, a factory is probably new. Or the crew is still learning. Now they install the larger buttons. These have more volume, and the edges stand farther out. Each one needs several hammer strikes to seat fully. Look closely, and you can see heat waves rising. Zoom in further, and the effect is clearer. So this work is never easy. It is a race against time. If one button does not seat right, there may be no time to reheat it. This is the bit after heavy use. Even one carbide button can cost over $100. Its recycle value is far lower. Sometimes it is worth just above scrap steel. Even so, recyclers still want worn carbide.